Okay, so welcome everybody to the third part of our tutorial on similarity casting. My name is Akis Spiropoulos, and I'm gonna try to explain to you why recommendations come into the picture when we're talking about similarity casting. So first of all, why am I be interested in recommendations? Because, you know, a lot of the items that we're thinking about caching or not caching are similar and unsimilar. In fact, the requests that we're making actually are heavily driven by recommendations from popular platforms. So Netflix, for example, reports 80% of these requests come from recommendations, YouTube something like 50%. These are pretty big numbers, right? So how do recommendations come into the picture? Imagine a user that is watching this red content here, and then normally, you know, below or next to this content, there's a couple of recommendations. Let's say the blue and the yellow content, right? And there is sort of a casting network. You have a local cast that fits here these two contents and a remote cast that fits everything. So far, right, the problem that we're trying to solve in Emilio's presentation was, well, given that each of these contents that I can cache here actually could satisfy requests not just for themselves, but for other contents as well, right, similar ones, then what should I cache, right? How should I change my caching policy, static and dynamic? But now, let's assume that, you know, what is in the cache is given and I cannot touch it, right? Then what would happen? Well, here in this case, right, if the user clicks one of the two recommendations, then, you know, neither one of them is locally cast and it leads to cache miss. So this is bad. But maybe, you know that the green content is locally cast. If the green content, for example, is similar with the blue one, I could replace the green content, the blue content recommendation with the green content, in which case what happens if the user requests the yellow one, you have a cache miss, but if the user requests the green one, then you have a cache hit. So you have improved your expected performance by making sort of this modification in the recommendations, right? So the name of the game when it comes to recommendations is, given what is cast here, how can we actually modify the recommendations in order to favor the things that are locally cast, right? And of course, you might be thinking, wait a minute, this guy is evil. He's gonna change all our recommendations and force us to watch garbage, you know, just to help the big network. But clearly this is not the case, right? Why this is not the case? Because, you know, even if I wanted to do that, I cannot, right? So, you know, imagine that you were just watching a clip by the Beatles. I can recommend to you another clip by the Beatles. This would be very, very related and you should be happy. I could also recommend, you know, like some other classic rock song. So this should be similar enough, right, to make the majority of people happy. But if I recommend something totally irrelevant, right, unless your kids just, you know, took your tablet away from your hands, there is no way that after this you would actually click this content. So even if this were cast and I wanted to recommend it to actually favor this, you know, you wouldn't click on it and I'm not gaining anything by a bad recommendation. So in fact, the idea is that, you know, for each of these contents, there are a lot of things that are in very close distance, right? Very similar to what you might just be watching right now. And there's a bunch of other things, even more, that are, you know, can be close enough, right? So if some of these contents are actually cast, then with recommendations, I could actually basically try to favor some of these cast contents without really you experiencing any, let's say, quality of experience degradation. Okay, so this is the idea of you know, why we want to make cast-friendly recommendations. What I'm going to talk about mostly, right, is this. This is topic 1, how to modify these recommendations to favor cast items. I'm going to touch just a little bit, right, on the next reasonable step, which is we saw caching, we saw recommendations. So how could we put this together, or can we put this together? And I'm gonna very briefly introduce a couple of other extra twists, some open problems, and we can discuss them more in the Q&A. Okay, so we start now, we need a model, right, for the user. So the model of the user that we assume is that the user will watch multiple clicks, right, during clips during a viewing session. And in fact, what we're watching is driven by recommendation, right? You're watching, let's say, this clip, then you have some recommendation, you click something here, then you watch something else, and so forth. So the system has memory, right? So whatever you're going to recommend now, it's not just going to affect what you're going to watch next, but potentially, right, what other recommendations you might get, and what you might actually watch after 2 steps and so forth. So how do we model this? Well, we go back again to this sort of similarity graph, where essentially here what I have is a content catalog. This, vertices are the contents. A link implies that content B is related to content A, right? So I could recommend content B after A, I could recommend C after A, but I couldn't recommend, let's say, content G after A because these two are not related. And then if I put everything together, I have this graph. This graph is actually input. It comes from the baseline recommender, and you can use, whatever state-of-the-art recommendation system you have there, running by Google or Netflix or whoever. Right? So this is input for us. We're not trying to compete with the baseline recommendation. What we are trying to do is that on top of this, given that we have this graph, and given also that we know that some of these contents here are cast, I denote them here with dark color, then the question is, what should I be recommending at every step of the user? Like assuming that the user is at B, what should I recommend? Assuming that the user goes at E, what should I recommend? So how do I denote it here? Imagine that the user is at content B, and imagine that I chose as recommendations C and E. Then basically I denote this with these two red arrows. These are my choices, my controls, and I also will have some control variables, RBC and RBE, that I will set to 1, for example. This could be discrete. In fact, in the first part, we're going to be looking at this as probabilities between 0 and 1. Right? So we make these recommendations, and then let's say the user clicks content E, moves to this part of the graph. Then we make this choice for the recommendations, right? G and H. And in fact, if the user clicks on this content, then we have a cascade. So that's great. What also might happen though is that at some point the user might not follow the recommendations, might go to the search bar and just pick something else, like slightly related but not included in this list, so totally unrelated. We assume that this happens independently with some probability 1 minus alpha. And whenever you do it, you just sort of teleport back into the graph into some random, let's say, content with a probability PF that you also know, right? So far, we're going to be assuming that we know all these things. So if you have this model, right, if you guessed that, this looks like a Markov chain, you're right. This is basically a Markov chain. So in fact, what we have is that we have this input graph, right? The user navigates this input graph according to the recommendations that we do, and how it navigates it according to this Markov chain, right? That has a random walk part and a teleport part. So our goal basically is, given this input, to figure out these red arrows, or basically to optimize this matrix of variables. And this R is basically the probability of recommending content J after user has watched content I. And how do we actually choose this? Our goal at the high level is to actually make sure that during the session of the user, we maximize the expected cascade rates, right? How do we do it? Again, someone might say, oh, well, what if you cheat and actually at every content you just recommend cast items, right? And until you exhaust me, and then eventually I click something. Well, the answer is that there is a number of ways to avoid it. One very simple one is to just impose an explicit constraint that says, whatever you're going to recommend, multiplied with, the similarity distance, it has to be, the similarity, not distance. This is, high when you actually have similar contents, low when you're dissimilar, then this has to be high enough, right? So this is basically now, let's say, the model, right? We have our model, we have the control variables, we have the constraint. What we're missing here, right, is the objective. Like, how do we actually convert these words here into a mathematical model that we can optimize, and which is a function of the control variables? So the way we're going to do it is, doing some sort of stochastic modeling, stochastic process analysis. I'm not going to dwell on that. For those of you that are familiar with stochastic processes, in fact, if you look at the session of the user and you assume that the user basically, starts from a content 1, follows the recommendation in the first step, recommendation in the second step, then in the third step, it teleports back somewhere to the graph, then again, recommendation, 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 search bar, then again, recommendation. Then it's easy to see that basically this session, this Markov process actually renews, right? Every time you go to you do a teleport step, which means that we can use the renewal reward theorem to calculate the expected cost of the entire session based only on the expected cost of a renewal cycle. And how do we get, the expected cost and the expected duration of a cycle? We just applied the absorbing Markov-Chain theory, where we assume that we have absorption at every step, at every state where we might be probability 1 minus alpha, and it's relatively easy to get. Okay, that's great, right? And where does this get us? This gets us actually now to a proper and clean optimization problem, right? Where we have here our control variables, we have our objective as a function of them, and we have a couple of constraints here. This is a quality constraint. This just makes sure that we recommend exactly n items, right? Whatever n is going to be. So what is this C here? This basic problem is saying, if you figure out this recommendation, what you want to do is to make sure that the expected cost, right, this is the expected cost of a session, is small, and this CI, right, is the cost of delivering content I. And this is actually fairly generic, right? So for example, if I had a single cast, I could have set CI equals to 0 if the content is cast and 1 if it's not cast. If I have a hierarchical cast, then I could assign different costs in its, let's say, level of the cast. But in fact, the CI could actually come from other sources as well. It might relate to monetary cost, congestion, all sorts of things, right? Does not just have to be casting. Okay, so we have this model. It's fairly generic, right? How do we solve this problem? It doesn't look that scary, to be honest, except, you have this matrix, and you have this inverse of this matrix, the control variables. However, the bad news is that in fact this problem is non-convex because these metrics are, if it was positive semi-definite, then in fact you could turn this into an SDP. However, in our case, it's not necessarily. So as the problem is right now, it would be non-convex and hard to solve, right? So what can you do? Well, the first thing that we did was, okay, we've all read Boyd, we go to chapter 3, you have all these little tricks to do, change of variables and transformations. So we say, you know what, we're gonna get rid of this annoying part here in the objective with the inverse of the matrix. Who needs that, right? We're gonna set this whole thing here equal to Z. And that creates us a beautiful linear objective. So, our troubles are over when it comes to here. It also introduces another constraint though, which basically says that, the new auxiliary variable Z is equal to this term, which if you unfold it gives you this constraint, right? So piece of cake, right? Well, not really, because in fact, okay, we don't have the problem now in the objective, we just moved it here in this constraint, where you have basically a non-affine equality constraint, which makes the problem non-convex. In fact, this problem is bilinear, which sounds easier than it actually is. So we're not there yet. But with a bit more thought now, actually we managed to come up with another transformation of variables here. I will not get into the details. What you need to keep from here is that in fact, if you do this extra transformation, you can also convert all the constraints to linear constraints. And this is an equivalent problem to this one, right? We didn't approximate or see it anyway. If you find the optimal solution here, then you can go in a one-to-one relation to the recommendation variables here. So this is great. We have a linear problem and we can solve it efficiently. So now we know how to, let's say, bias recommendations towards favoring cast content, and in fact, in an optimal way that would minimize the expected cost of a session. Okay, that's great. And, we have done some simulations also to see how it works. I'm not going to dwell on this. I can come back if you're interested in seeing some plots. What you need to, maybe just one number that I want to quote, is that, we managed to get, let's say, up to 10x improvement, for example, compared to a baseline where, what is the baseline? The baseline is basically a recommendation algorithm that was doing the original recommendation, what, let's say, YouTube would think in the first data set, without actually trying to favor cast content. And we have used, to do that, we have used a number of real data sets, right? Either the ones that we found and pre-processed, or actually some of them we collected ourselves. And these data sets give you these similarity distances, right? Based on which you actually can make these recommendations. So this is great. right? We have now a very useful tool. We have a convex optimization framework to solve these problems. In fact, does it solve only problem? Not necessarily, right? You can actually try to introduce additional twists into this problem. In fact, one thing that we did is to introduce position preference, right? So what's position preference? It's the idea that basically, you know, if I have a list of recommendations here and it's long, it has been experimentally validated that users actually have a much higher chance of clicking whatever you have higher up the list than something that is further down the list. It seems kind of obvious in retrospect. However, in our previous model, we have been assuming, right, that the click probability, given that I follow the recommendations, is just uniform, 1 over n. So what happens if I want to introduce different probabilities that depend on the positions and also make the recommendations conditional on which position I make its recommendation? Then, you know, life gets a little bit more complicated, right? Now I have these probabilities. I also have here a tensor as my control variables rather than a matrix, because the third dimension is the position where you're going to make this recommendation. But the good news is that, okay, despite the seeming complexity and clearly a little bit larger problem, this can also be converted to NLP, right? And you can solve. Okay, so this is great, right? Does it mean that this is the only way to tackle these problems? Not really. Does it mean that this is the best way to tackle this type of problems? Again, not necessarily. It depends, right? So this approach that I have presented has 3 shortcomings, at least 3 that we have, let's say, identified. The first one is that I kind of lied to you when I was saying that this finds the optimal solution, right? In fact, it finds the optimal solution under the assumption that the user session is infinitely long, right? That the user accesses a lot of, you know, contents one after the other. And you might have guessed it because at some point to get my objective, I use the renewal reward theorem, which we know that it's, you know, it's only asymptotically correct. So in fact, I know how to actually solve the problem optimally with this methodology for very large sessions. I also, you know, it's kind of easy to actually have a very one-step session, right? You can come up with a greedy algorithm, but what happens in between, right? What about any arbitrary session length in between, whatever means, you know, very long here and just one step? So we don't have an exact optimal solution for this. The second problem is that even though, you know, after a lot of pain and sweat, we converted this problem to NLP, right? If the content catalog starts becoming large, right? Imagine thousands of content, which is not even a very large catalog, will imply 1 million recommendation variables that you have to optimize with SLP. So things start getting quite slow, right? As you increase the content catalog size. So, you know, is there a way to fix this? And last but not least, you know, the model that we have with for the user about, you know, how the user reacts to the recommendation that we have, it's pretty simplistic. In fact, we're assuming that the user, you know, closes her eyes, decides, okay, in this step, will I follow the recommendations or not? This happens independently with the probability alpha. And then if I do follow the recommendations, then, you know, I'll pick its content uniformly or at best showing some position preference, right? But it doesn't depend on the actual quality of the recommendation that I just made. In some cases, this could be a valid assumption. In some other cases, it's not. So the question is, can we actually beef up our model, our user model a little bit? So the answer is that, yes, there is a way to actually hit all these, let's say, birds with one stone. And this stone is Markov decision processes, right? And in fact, I'm guessing a number of you we have been thinking about Markov decision process. Since I have a problem that is basically trying to control a Markov chain, right? You know, the natural way to go to do multi-stage control over such a Markov chain is, of course, Markov decision process, right? So we tried this a little bit more recently. So the first step, if you want to apply this, is to try to reformulate the problem that you're trying to solve into the MDP framework. I'm not going to go into too much technical details here, but the basic step, you know, you can write down the Bellman optimality equation here as a function of the controls that you're doing, right? Again, the red variables, the recommendation. Now, what is this Bellman recursion? For those of you that might not know, Well, what we have here is, let's say, the optimal session cost, right, starting at a given content I, is equal to the instantaneous cost, right, of this content I. So, for example, if the content was cast, you could set it to 0. If not cast, you could set it to some value, which is the fetching cost. And then I have what is called the cost to go term, right, which is the remaining cost of the session as a function of the recommendation variables that I'm going to choose and as a function of the user behavior, right? So this Pij now is the Markov chain, right? And it's a Markov chain that depends on how exactly you, what exactly recommendations you do. But this is now fairly generic, right? So in fact, in here, I could have a model that recreates the scenario that I had before, but I can also introduce now different user behaviors and still I can solve this type of equations, right? And the key here in this formula is that, you know, I'm looking for these variables for every I, and this actually show up in here. So I have a system of equations that, that I could solve in a number of different ways. You can do value iteration, or you can do policy iteration. In our case, we did policy iteration. Okay, so we have now this reformulation of the problem. Why is this more useful than what we had before? Well, first of all, in fact, if I have an arbitrary session length, right, and I know what is the mean session length of for a user, then in fact, I can tune my discount parameter here to match this mean session length, which means that now I can actually find the optimal solution for, you know, shorter session lengths, medium session lengths, longer session lengths, and so forth, not just the limit. Okay, so this basically solves issue 1, right? In a very simple way, let's say. The second thing, the second concern that we had to do with complexity, right? So let's see, what is the complexity of solving this problem? Well, in fact, if you consider a vanilla MDP, right, usually you have discrete state here, right? All the contents that, that you might have, let's say the total number of contents is K, and also you have your action space, which is normally discrete as well. So what are the action space? If I had, let's say, a catalog of 1,000 content, and I have the, you know, I need to make 3 recommendations for each content, then basically what I need to be doing in here is to figure out all the combinations of 1,000 contents into 3, right? And evaluate the cost to go for each of these combinations, right? And find the minimum. So the heavy operation is this one. And in fact, you know, if you actually solve this problem in the normal way, right, with discrete actions, then the complexity of this problem might actually be worse than the previous problem that we had with ELP. However, we do not despair. There's a couple of tricks that we can do. And the first trick is that, again, we don't necessarily have to actually have discrete action space. We can, in fact, again, work with recommendation probabilities in continuous, let's say, space. So, in fact, we might say, OK, let me try to solve this, trying to find here, right, the recommendation probabilities between 0 and 1 for every content that I might be interested in recommending. Can I do it? Yes, the answer is I can do it. Does it help? Yes, it helps because A, right, this minimization now, where you have to do an exhaustive search of all the possible combinations, now to find this, to solve this problem, this actually turns out to be an LP, right? So this you can solve much faster than this exhaustive search, especially as, you know, N and K become larger. And in fact, it's a smaller NP than before, right? Because we are actually now solving this Bellman recursion, we have decoupled the problem for each, let's say, content I where we might be. So we need to be solving one LP here for each content I, and this LP, in fact, is only in the size of K variables, not K squares. So this actually will give you a lot of performance advantages, but, you know, this is, I'm just saying this, right? So perhaps some results will convince you. And, you know, this is what we're plotting on the y-axis is the execution time, right? And as a function on the x-axis of how large the catalog is. And the dark line here is the previous scenario, the LP formulation that we solved with simplex. And here with the blue curve, we are solving the same problem, the same user behavior, but now through the MDP. And you see that the performance advantages are very, very impressive. Right? So in terms of complexity, this might be the biggest advantage of this, let's say, MDP framework compared to the convex optimization one. Okay, so this solves then issue 2. And in fact, issue 3, if you remember, was the user model and how realistic it is. I'm not going to go into the details of this. You can go to the paper, but just high level is that in addition to the previous user that we were able to model with a convex optimization framework, here we can model a bunch of other, let's say, interesting users and also find the optimal solution for them, which we couldn't with a previous framework. So for example, we have here a picky user, right, where the probability to click a given content M depends on how related content M is, right? So whenever I say a bunch of recommendations, I'm going to evaluate how relevant these recommendations are to me, and I'm going to decide if I want to follow recommendations altogether. And then also between the things that I recommended, I can be picky, and I'm going to try to pick things that are more, let's say, related with higher probability. And so this we can solve, we have in this paper, and this actually solves issue 3 as well, right? So this is great because now we have two sort of analytical tools that we can use to tackle these problems of cache-friendly recommendations. And we can actually introduce a number of twists into either one of those two, right? So what is missing? A number of things are missing. First of all, we have been assuming that a lot of this information, right, all the parameters about the user behavior that we know and that they're static, right? And in many cases, this will not be the case. So what if we didn't know some of these parameters? Then the first natural approach, right, to go about this problem is to turn our NDP into a reinforcement learning, let's say, problem, right? That's a natural way to go. In fact, we have worked a bit in this direction. It works quite well when it comes to the action space, right? To reducing the complexity on the action space, we can still play with probabilities there. But in fact, in principle, if you want to solve a large problem with a large catalog, let's say of 1 million content, you really need to have some good state value approximation with some neural network approach. So you need to go to deep reinforcement learning. So this problem is more or less open. The second approach that you could take, which is you know, more powerful and more simple at the same time, so it depends on the setup, is that if I had a user behavior that is non-stationary or adversarial, you know, you have a user that gets pissed off, for example, if you actually make a lot of bad recommendations and you don't know this in advance, right, what kind of mood they might be, then you could actually try to use a framework like online convex optimization, right, where the idea is we go back to the framework that we had before, the convex optimization one, but now we assume that some of these parameters here are unknown and they appear at every, let's say, instance of time. And our idea is to try to figure out the policy and also the model in some sense with a dynamic algorithm. And you know, this is the online convex optimization framework. You have online gradient descent by Zienkiewicz that solves this type of problems. And in fact, if also your constraints, right, about quality, they're also adversarial or unknown, then there is line of work there that tackles this, these problems by Mike Neely and a lot of other people who've worked on this as well. Okay, that's one interesting direction, right? This is also open. What else? Well, now that we have been looking for a while on the recommendation problems, right, we can go back and think about the caching problem again, right? Which is, okay, so Akis has shown how to deal with recommendations, Emilio has shown how to deal with caching, so why don't we put these two together and see if we can do better, right? And the first question is, can we do better? Yes, you can have some very simple examples that show that you could do better by jointly optimized. So imagine here this original setup that I had where, you know, the dark arrows are the, you know, the similarity graph. And then the red arrows is what you are able to recommend. Here I have these two items cast here, the I and H, right? And then you see that in this case, you know, the best that I can do is just a few arrows reading to dark contents, the cast ones. However, if I had the option to choose which of these nodes to actually cast, right, then clearly a better solution will be to cast this item C here. Why? Because I see a lot of incoming arrows here, which means that if this guy was cast, then I would actually be able to recommend this for a lot of other contents, which just visually I predict that would lead to a higher expected cast hit rate, right? So in fact, the idea here with joint policies is, we still want to recommend content that leads to cast content, right? So you have this set of control variables, but now you also want to cast content that is convenient for these recommendations, right? You want to have to cast contents that could be recommended to many users, right? Or to many other, could follow many other contents that different users have seen. Okay, so this is great, right? It sounds promising, but the bad news is that in the continuous domain, right, if I have my control variables, the recommendations, and the caching to be continuous, this is an open problem, right? So how do you do joint caching and recommendations in this setup where you have sequential content accesses? We don't have a solution for this yet, right? So does this mean that we cannot solve joint problems? No. In fact, we have worked quite a bit on joint recommendation and caching problems, but we need to simplify a little bit the setup. So we need to go back to the simpler caching setup from femto caching, where in principle, each of these users, right, draws either one request, right, from some underlying probability, or if you join many requests, this RIID. You don't have now this, let's say, dependency from one content to the next one. So if you look at the vanilla scenario here, in the standard femto caching, you have different users here that are connected to different base stations, so they also have access to these caches and the items that are there. And the idea here in the well-known paper by Sarmungan, Dimakis, and Kaire is what do I cache in each one of these. And this problem is NP, but in fact, you can actually approximate it quite well with a greedy algorithm and by using, some modular maximization theory. So that's great. And then what about similarity caching? Well, similarity caching basically says that, okay, you know what if in this context by caching content 3, right, not only could I satisfy a request for content 3 by this node, but I could also maybe satisfy a request for content 5 if 5 is similar, right, to content 3. So this is the idea roughly behind similarity caching. So now the idea is, how do I change my policy to actually take this similarity into account? And this problem, you can also approximate using some modular maximization and theory and greedy algorithm, right? And the question that we wanted to figure out, okay, what if in this problem, we actually introduce an additional control variable, which is the recommendation. So let's say now that we have, again, the recommendation variables, in addition to what is cast in each of these caches, we have a recommendation variable that tells us whether we will recommend or not content N to user I. And on what grounds are we going to make this decision? We again have some, let's say, utility value that tells us, right, how interesting content N is for user I. And this, let's say, is the probability that user I will click content N. So how does this problem look like? This looks in a simple version, let's say, or maybe in the simplest version, it looks like this. It might look scary to some of you if you're familiar with the femto caching framework, not so much then, right? It's not so scary. And in fact, what this thing is saying is the following, right? I want to maximize, let's say, the cache hit rate by controlling both sets of variables, what is cast and what is recommended. And the key term is this, right? What does this term say? It says that, look, if I recommend content N to user I, and user I is interested in content N, and this content N is cast in a base station J, and this base station J is within range, right? Is accessible by user I, then all these variables are equal to 1, and then 1 minus 1, this thing is 0, so this entire product is 0, and we have one cascade. Victory, right? So in principle, what this thing is doing is actually taking into account also the orientation, the user taste, the connectivity, and basically tries to count the cascades. So we have now this objective. We have our usual constraints like math-theoretic constraints for the capacity and this constraint for the recommendations. And we can try to solve this, right? Well, there's some bad news and some good news. First of all, the bad news is that even though, all these objectives that we were looking in, in femto casting and similarity casting, you can show relatively easily that they're submodular, right? Now that we have an additional set of variables, if we want to do a vanilla, let's say, greedy algorithm, and we try to show if this function is submodular in the joint set, right, of both variables, the answer is that it's not. And it's pretty easy to see with a counterexample why it isn't. I can actually show you offline in the Q&A. But this means that basically if I apply a greedy algorithm and I start picking recommendation and casting until, I run out of options for recommendation and casting, right? I feel like my classes and etc. Then this is not going to work. You might get a very, very bad solution. You have no approximation guarantees. Does this mean that the game is over? Not really, right? We have a paper recently that actually manages to solve this problem. And what do I mean by solving? First of all, let's say, again, high level, I can go back to the Q&A, but the idea is that, we had the joint optimization, but if we define a function just in the set of the x variables, right? And then for each kind of x, we go and solve. So this, let's say, optimizing with respect to x is an outer problem. And then we go and try to optimize an inner problem for every possible x. We find the maximum, let's say, value of this and the recommendations that give this. Then we can say a number of useful things about g of x. First one is that g of x can be solved in polynomial time for any x. So solving this problem is easy and you can solve it exactly. The second result, even more interestingly, is that this g of x is submodular in x, right? So if you put this together and, the well-known result that you can decompose this joint maximization, right, into sort of this outer inner maximization, then basically you can actually come up with a greedy algorithm. It looks like primal decomposition, right, because it has an outer loop and an inner loop there that is maximizing, but we've proved that this achieves an approximation ratio of 1/2, right? So basically this problem, and in fact, a number of twists, right, that we can have on top of this problem. So here you see I saw a different figure than before. We can solve. And we can approximate as before, despite the introduction of the new set of variables. And in fact, there is a bunch of other problems, right, that we can treat in the same way. We have been looking into transcoding, and in fact, this fits the framework and we can get the approximation guarantee. We have been looking at routing and user association variables. Here, things get complicated, and this is an open problem. Emilio already mentioned a little bit about routing. And there's other things that you can imagine putting in this framework. Okay, and I want to finish basically with two directions that go into kind of different ways, but are very interesting in this whole line of work of similarity casting and cast-friendly recommendations. The one is basically the following. If we ignore the algorithmic part and we just look into the similarity graph, right? We have a data set and we look at the graph itself of things that are similar to each other, right? What can we say about the performance of, let's say, similarity casting or joint casting and recommendation? So we did some preliminary work recently, and we found some quite interesting, let's say, results. The basic idea, and again, ask me in the Q&A if you're interested in this thread, but the idea is that for those of you that know complex network theory, is that properties of complex networks like skewed degree distribution, community structure, etc., that seem to affect a number of processes on top of this complex graph, seem to play a big role as well to predict the performance of what's going to happen, right, if on top of the similarity graph you try to apply, this type of algorithm. So you can actually make predictions without ever running these algorithms, right? That's the first thread. The second thread that is quite interesting is experiments, right? All these works have been based on the premise that, the users are willing to actually watch something similar, if this similar thing is similar enough, or maybe if this similar thing actually can be given with better quality. So we've had the threads of real experiments with some colleagues where we're actually trying to basically check with users, real users, and see if this is true. And what we're doing is we have a YouTube proxy where we can actually modify the recommendations to bias them towards cast items. And also we can modify the quality of streaming, right, by introducing some perturbations, etc. So this is really interesting work. The initial findings actually are very promising for what we have been assuming for all the fun theory stuff. And again, I can talk more about it if you're interested. Okay, and this wraps up my my presentation. Here is some publication of ours, some references if you're interested in specific work, and I'm very happy to take questions right now. Thank you.